really pleased to have Swee Hong Chan, who's in his third year as a member of the Mid-Atlantic Combinatorics Geometry and Algebra community at Rutgers. He'll be telling us about log-concave inequalities for matroids. So,
thank you so much for the introduction, Joel. And I will first thank the organizer for arranging this wonderful conference to bring everybody together. I would also like to thank everybody today for coming. And today, the main characters is log-concave inequalities. And here is what I mean by that. So for today, our sequence A1, A2 up to AN will always be non-negative integers. Okay? And we say that this sequence is log-concave if, for any case strictly between 1 and n, the square of the kth number is greater than the product of the neighbors k plus 1 and k minus 1 number. Okay? So for example, this sequence here is a log-concave sequence. It is because, well, we can check it by direct calculation. 9 squared is 81. 81 is greater than 4 times 15, which is 60. And that is as far as that's the limit of my arithmetic ability. Yes. So one of the earliest reasons why people start studying log concavity is that because log concavity and positivity, it implies unimodality. So this means that this sequence which first increases up to a certain point, decreases, and then disappears. Okay? And of course, after that, we find many other reasons to why you want to study log concavity. And here is an example of a log-concave shaped object in real life. This is the Cheongmachong Burial Mound in Gyeongju, South Korea. I visited there 2 months ago, and according to the local expert, they told me that this shape is a natural shape if you try to whenever you try to build a burial mound. Okay? But anyway, enough about real life. Let us come back to mathematics. Okay, and the first, maybe even the quintessential example of log-concave coefficients, log-concave sequence, is the binomial coefficients. So here n is fixed, k ranges from 0 up to n. And this sequence is log-concave is because it's because direct computation. You take the ratio of this number, you do the calculation at the train, you get that is equal to 1 plus 1 over k times 1 plus 1 over n minus k. K is between 0 and n, therefore this number is greater than 1. That's why it's a log-concave. Okay. Second example, it comes from permutation theory, where again n is fixed. Let ak be the number of permutations with exactly k inversions. And here inversion of permutation, is a pair I and j, where I is less than j, but pi I is greater than pi j. So you inverse the order. That's why it's called inversion. Okay, and already for this sequence, as far as I know, you cannot actually prove it's log-concave by direct computation. For the reason because there is no closed form formula for AK. Instead, what people usually do is that they first write a generating function for this polynomial, so a generating function for this sequence, and then they realize that, oh, what a coincidence! This thing turns out to be the Q analog of n factorial. So what it means is that this is the product of this polynomial of 1 plus q squared up to q to the power of I. And what is important here is that these polynomials, the coefficient is all 1. In particular, it's log-concave. And it's known that when you take product of log-concave polynomials, the resulting polynomial is again log-concave. That's how we know that this sequence is log-concave. Okay, 2 examples, and this is the last example for today. This one comes from graph theory. Let G be any given graph. Let AK be the number of forests with exactly k edges, where a forest is a subset of edges of the graph that has no cycles at all. For example, let's say that this is our given graph G. This is a forest. This is not a forest because it has a cycle. And when your forest is also connected, it's usually called a spanning tree. Okay. And unlike the other 2 examples, this proving the log-concavity of this sequence turns out to be an extremely hard problem. So it was first conjectured by Mason in 1972, where he actually conjectured not only for graphs, he conjectured for all matroids. I'll explain why it's matroid in the later slides. And this problem was open for around 72 to 15 is 43 years. It was open for 43 years before it was finally solved by Juniher in 2015 by using this technique that we now know as the combinatorial Hotz theory. Okay, so this result and this theory was cited by International Mathematical Union in 2022 as one of the reasons, among many reasons, but still one of the reasons, to award Juniher with Fields Medal in 2022. Okay. Up till here, everything good so far? Like the examples is good? Okay, so now we have seen three examples of log-concave inequality. The first and second one is at the level of a homework exercise. The third one took almost 50 years and the work of many great people, including a field medalist, to finally completely solve the problem. So intuitively, it is very, very, very clear that the third inequality is much more difficult than the other two inequalities, right? But for now, let me just play a devil's advocate. Let me just try to be very contrarian, okay, for 1 minute. Hey, Swee Hong, maybe there's actually an easy, almost trivial solution to the third problem. It's just that nobody good enough has worked hard enough to find it, right? After all, everything in combinatorics is trivial. By the way, I completely disagree. I completely disagree with what my legal advocate just said. Okay? But we are all mathematicians here, right? If you disagree with somebody, we should not go to Twitter and say that you are wrong. That is not how mathematicians do things. What we should instead do is that we should give a rigorous argument. We should give a rigorous justification why the third inequality is more difficult than the other two inequalities. And that is the goal that we are trying to do today. That's the goal that we are trying to do today. Yes. Okay. Up till here, is everything good so far? Is the motivation clear? Okay. Thank you. And before I proceed, let me just actually apologize to everybody here that unfortunately, I still don't know how to show that the tree is more difficult than the other two. So what I aim to do for today is to do the next best thing, which is that a slight generalization. So something a bit more general than the third inequality can be shown rigorously to be strictly more difficult than the other inequalities. And we'll do so by using the tools and ideas coming from computer science, coming from complexity theory. That is what we are going to do today. Okay. Everybody happy? Okay, let me get some more here before I continue. Okay, so if everybody is happy, then let me continue. Let me continue to discuss what is this generalization. And to do that, I need to define what this thing that's called matroids. Okay, so a matroid, this is a pair of two things. First thing is a ground set X. For today, is always a finite set. We are not going to do infinite stuff today. Okay, and the second one is a collection of subsets of the ground set that's called independent set. These independent sets need to satisfy true properties that we will explain in the next slide. But for now, let us just see two examples, just so that we have something concrete in mind, so that things are not very abstract. Okay, the first example in mind should be the graphical matroid. This is when the ground set X is a set of edges of any given graph, and your independent set will be any set of 4S, any set of edges that do not form a cycle. So this is the example that we saw in the third inequality. Another example to keep in mind, which is actually arguably is the reason why people start studying matroid, is when the set X is any finite set of vectors over any field F. The field F can be finite field, can be infinite field. And I think for today, what will be important is when the field is when it's a field of size 2. So binary matroid. And the independent set is, pardon the pun, is a set of linearly independent vectors. Okay. So these are the two examples of matroid. And here are the two axioms, two properties that all matroids need to satisfy. The first one is called hereditary property, or called the subset property, which says that any subset of independent set is again independent. So for example, this is a 4S, so it's independent set. Remove any edges, the resulting set is again independent. And in a different language, sometimes we call this as this means that all matroid is actually an abstract simplicial complex. Okay. And the second property that this matroid needs to satisfy is called the exchange property, which says that if you have any two subsets, any two independent sets, and one of them is smaller than the other in terms of size. So that means that the cardinality of one set is less than the other. In that situation, you can always find the element X in the larger set, let's say these edges, move it to the smaller set. The resulting set is again independent. The resulting set is again the forest. Okay. So at the first glance, when I first studied this thing, I find that this seems very abstract. But nowadays, I like to think about these axioms as a way to capture almost all, or maybe almost all important properties of vector spaces. So all vector spaces, this is like the abstraction. There's an abstract version of a linear algebra. Okay. And following that idea, just like linear algebra, a basis, what's a basis? Basis is a maximal independent set, and that is the same for matroid. And the rank of a matroid is simply the size of larger spaces, just like in linear algebra. And it can be shown that this R is actually well defined in the sense that any maximal basis, any maximal independent set has the same size. Okay, up till here, everything clear so far about matroid? Everybody happy? Okay, good. If everybody is happy, let me continue. Okay, now that we understand matroid, I can now state the more general version of the third inequality that we saw, the one that proved by Junyi. And this one is now is known as the Mason's conjecture. So given a matroid M, let Ik be the number of independent sets with exactly k elements. So in the case of graph, this Ik will be the number of forests with exactly k edges. So that is our third inequality. And the log concavity of this sequence was first conjectured by Mason in 1972, where he believed that this sequence is I1, I2 up to In is a log concave sequence. In fact, actually he made many other, in the same paper, he made many other conjectures, but today we will only focus on this one. Okay. And for the 40 years, this conjecture is virtually unsolved until in 2015, Junhe managed to finally prove it for graphical matroid. And in a series of work after that, together with Adipasito and Katz, two of his co-authors, they finally proved this for all matroids. Okay, and both of this, all of this proof now, all the idea and techniques is now called the combinatorial Hodge theory. Okay, and yeah, and so now between 2018 and 2000 now is 2024, right? So in between these 6 years, fortunately, many mathematicians have looked at this conjecture again, and there are now, I think, at least 4 or 5 different proofs now of this result. And today, I want to focus on one of them, which is viewing the Mason's conjecture as a special case of a slightly more general inequality. Okay. And this inequality is called the Stanleyian inequality in the literature. What is this inequality? So for this one, we change our view a little bit. Rather than focusing on independent set, we focus on the basis, which is the maximal independent set. And for here, let us fix a subset S of the ground set. Let Bk be the number of bases of the matroid, such that the element coming from this special subset S is exactly equal to k. Okay. And I will also rescale this number Bk by some binomial coefficient. This is just some natural steps. There's no need to worry too much about that. And the Stanleyian inequality state that this sequence B1, B2, B3 up to Bn is again a log concave sequence. Okay. And this inequality, the reason why it's called Stanleyian inequality is actually because it's proved by 2 different people. The first one is by Richard Stanley in 1981, who actually proved this not for all matroids. He actually proved this only for regular matroids. And in fact, this is one of the rare. So between this, after Mason's conjecture, between 1972 and 2015, this is one of the rare papers that actually did publish something and try to attempt to prove Mason's conjecture. Okay. And his attempt is Stanley explained like this. These numbers, you can interpret it as the mixed volume of some polytopes that's called jonotops. And then the log concavity follows as a special case of the Alexandrov-Fenchel inequality in the mixed volume theory. And in hindsight, this idea of viewing all of this number as a geometric object is like in a way, it's a prototype to what Junhe had actually proved the Mason's conjecture, which is to fill all this number as in the Mason case, is actually the Milnor's number for this thing that's called a Taylor manifold. Okay, and this was proved by Stanley, but only for the case of regular matroids. So in particular, it will not apply to the graphical matroid after some conversion. Okay, and in 2023, this inequality was finally proved for all matroids. This is by Alan Yen in 2000. He was a junior student in Princeton. He is now a graduate student in Harvard. And he proved this by this method that is now called the Lorentzian polynomials, which is you can think of as like the polynomial version of Potts theory. Okay. Up till here, everything clear about the inequality, about the theorems, about the history? Good. Okay. Okay. Sorry, let me so as I mentioned before, right? The Stanleyan inequality, you can view it as a generalization of matroid. In fact, by using this Stanleyan inequality, we can now give one-page proof of the Mason's conjecture. Yeah. Or let me also just say that the first proof of Mason's conjecture is actually the first one that they published by Adipasloho and Katz. It is actually 70 pages. But nowadays, now we can do it in one page. Okay. So the proof goes like this. So we will need to define this thing called the direct sum of matroid. This is the analog of direct sum for vector spaces. So given two matroid M1 and M2, let M prime, this is direct sum of M1 and M2. This is a new matroid where the ground set is a disjoint union of M1, the ground set of the M1 and M2. And the independent set is, as you might have guessed, is also the disjoint union of any two independent set of M1 and M2. Okay. And now, let us prove Mason's conjecture. Let this M be the original matroid in Mason's conjecture, and I introduce a new matroid F. This is a free matroid. This is a matroid with R elements. R is the rank of M, and this thing is free, means that every subset of this matroid F is independent. We define it, and you can check that this is actually defined a matroid. Now, M prime, take it to be direct sum of M and F. And the S that appears in the Stanleyan inequality, take this to be the ground set of M. Then it follows almost by definition or almost by construction, if you want, that the number Ik for the original matroid M is now equal to the number Bk for the new matroid M. On the other hand, by Stanleyan inequality, we already know that this Bk is log-concave, right? And therefore, it follows as a special case that this Ik is also log-concave. And that proves the Mason's conjecture. So this is how to say a 3-slide proof, or maybe if you write it in a paper, then it's like a, depending on the margin, 1 paragraph. Okay, 1 paragraph proof of the Mason's conjecture.
You should go back to the slide with the Stanleyan inequality.
Yes.
Thank you. The regularity was.
Yes, the regular was proved by Stanley, and the general case was proved by Alan Yen. And in fact, actually, I think that maybe just let me mention that actually just like 2 weeks ago, somebody actually managed to use this Stanleyan inequality to prove a special case of this Stanley-Steger conjecture. Not the whole thing. The whole thing is yes. For this log-concavity for the Eulerian polynomials for the with 2%. Yes. Okay. And any other question before we continue? No? Okay. And let me also mention that in fact the Stanley and Yen, they actually prove a more general inequality in the following sense. So introduce an extra D subset S1, S2 up to SD of this ground set X. Introduce also extra number L1 up to LD for this any positive integers. And suppose that now you count your basis in a more restrictive way, which is that such that the number of elements coming from S1, S2 up to SD is equal to L1, L2 up to LD. And it turns out that even with this initial restriction, this sequence BD1, BD2 up to BDN is still a log-concave sequence. And one reason why I want to mention this is that because to the best of my knowledge, all proof of this kind of inequality, there is no direct proof. There's no direct proof to prove the simple case. What they did essentially is that, or maybe implicitly, is that you need to prove this for D equal to any number first, and then you take D equal to 0. Okay? Up till here, any question about the general statement of standing inequality? Yes. Okay, okay, good. Okay. If everybody's happy now, let me go back again to be to my devil advocate mode, like to be a contrarian. So like, hey Swee Hong, I look at this inequality. You see that both the left-hand side and right-hand side, they have combinatorial interpretation. They are counting number or bases of some matroid with some properties. And so, an easy proof of this inequality without using all this Hodge theory, without also using all this Alexander-Purcell inequality, would be to give an injection. To give an injection, standing bases on the counted by the right-hand side, two bases on the left-hand side. And you want this this map to be injection. And that will give you a simple proof of the standing inequality. It will show how combinatorics are all trivial. Okay. And of course, in order to say something more meaningful about this, we need to have a concrete, or we need to have a rigorous definition. What exactly you mean by simple or nice injection? And the good news is that there is actually already like a more or less commonly accepted standard for what it means to be a nice injection. And in this case, usually it's called the combinatorial injection. The definition goes like this. An injection from A to B, we say that this injection is combinatorial if for any element x in A, you can the injection that gives, you can use it to compute the image fx in polynomial amount of steps. Here is polynomial with respect to the length of the input x. So you need to think like you are building an algorithm. You are writing an algorithm to try to, so that given any x, then your computer will tell you what is your output. And of course, then how fast it runs will depend on how long your input is, how big your graph is, or how big your process is. And for this to be an injection, it means that the inverse needs to be well defined, right? So what this means in our definition is that for any element y in the image, so any element y in the codomain, you first need to be able to tell if this is the image of your map. And if it is, you also need to tell what is the corresponding element in the domain. Okay? And of course, you also want this to be done in polynomial time. Okay? And understand the definition is maybe is a bit wordy, but let's see some example to see how it actually works. So this is the binomial inequality that we saw, like our first inequality. This inequality, in fact, has a lattice path interpretation. Okay? So you can interpret in the following way. Let A, B, C, D be any two integer point in the integer lattice. Okay? I define K, A, C, B, D to be the number of pairs of northeast lattice path. So that means that the path can only go right or can go up. It cannot go any other direction. This is the number of pairs of northeast lattice path from A to C and B to D. Okay? So let A, B, C, D be given by these four numbers over here. And again, by direct calculation, it follows that the left-hand side of binomial inequality turns out to be equal to K, A, C, B, D. The right-hand side equal to K, A, D, B, C. Okay? So this gives a lattice path interpretation of the binomial inequality. And therefore, if I want to give an injective proof of the binomial inequality, what we can do is as follows. Take any lattice path from the set K, A, D, B, C. Because of the position of A, B, C, D, because it's a two-dimension, this means that this path must intersect at some point, right? Now, find the first intersection. You swap the red and blue color. That will give you a new path in the set K, A, C, B, D. And it's not too hard to check that this is in fact an injection. And furthermore, this injection is actually combinatorial in the sense that this map can be combined in polynomial time. Why? This is because given any element, any element, you can draw this picture in linear time. Just draw them. And then you find the intersection also in linear time, right? It just keep walking from the blue color until you find the section. Then after that, you swap the color. Again, linear time. So something like 3n. In particular, it's linear. In particular, it is polynomial. So this map is injection. So this map is combinatorial injection. And to the best of my knowledge, so there was this list by Richard Stanley about this combinatorial interpretation or combinatorial proof or like injective proof of all of this inequality. And I try to check all of those that has been proved. And all of those that claim to have a nice injection, they all fall to this kind of injections. Okay, so that's okay. Up here, any question about definition of the combinatorial injection? Happy? Okay. Now that without further delay, here is our first result to make here is our first argument against our contrarian devil's advocate, which is that no matter how hard we try, there not only that there is no known there's no combinatorial proof, injective proof for standard inequality, we claim that it's absolutely impossible to find one. Okay, unless the MP to power MP relative to MP is equal to co-MP relative to MP. And at this point, I would like to actually, let's see how much time we have. Okay, at this point, I would like to apologize to the audience that depending on the time, I will not be able to rigorously say what this assumption actually means. So, but if we end up at having like a bit early, then I'll be happy to explain what this means. But for the purposes of this talk, I think it is sufficient, or maybe it's enough to think of this as a stronger assumption that P not equal to MP. Or if you want even more, if you want to explain if the how I will try to explain this to my parents is this: that if this assumption is wrong, then we win $1 million, or at least somebody will win $1 million, because this implies that P equal to MP, and that person or maybe somebody in the audience, or maybe the one that prove P equal to MP, then yeah, you will get the $1 million from the Millennium Prize. Yeah, in fact, actually, and I checked actually. So it's actually not true that if you disprove some of the conjecture in the Millennium Prize, you get $1 million. For example, in Riemann hypothesis, if you disprove it, yes, it is. I checked. In fact, it's recorded, so I cannot say who. I checked with one of the person who is in the committee. He said that it depends on the discretion of the committee to give you 1 million or not. So, for example, the reason is this. For example, if somebody just use a computer, like press a button and find a counter example to Riemann hypothesis, they might or might not. They might give you $500,000. They might give you the full 1 million. They might also just give you $1 for that proof. Yes. However, for P not equal to MP, they actually state in a way that they guarantee. If you prove P equal to MP, if you prove P not equal to MP, either one of them you get $1 million. Okay? Yeah, and of course I also asked them that what about if somebody prove that you cannot prove or disprove P not equal to MP? Then that one is not clear if you get $1 million or not. But well, that is. Anyway, any questions so far about the result? Yes, question?
When you say Stanley, is it the D equal to 0 case?
That's a good question. If you go to D is 0 case, we can guarantee it for D greater than 1, J equal to 1. In fact, just take D equal to 1 and it's already like that. For D equal to 0, it is still an open problem. In fact, if you can solve the D equal to 0 case, you will in fact solve basically solve every all other open problems in this area. Like you will know how to in fact go as far as you will go to solve the third inequality. Actually, we know how to do that. Yes. Any other question? Feel free to ask question anytime. Okay, happy? Okay. Okay, if everybody is happy, then I would like to continue this talk to talk about how we actually prove this result. How we can actually argue that there is no combinatorial injective proof. And I would like to argue, and the way to do it is that rather than working on this specifically, we should actually try to work on this level of generality in complexity theory that's called the sharp P. Okay, and here is how sharp P is defined. Okay, and before I go for the full proof, let me just go through some informal definition for intuition, just so that we have some picture on what it actually means. So sharp P, I like to think about this as the class of problems. It's the class of problem of counting the number of objects satisfying some properties, and these properties should be simple to verify. For example, a problem in sharp P will be counting the number of proper tree colorings of a given graph G. And the property here will be whether or not the coloring is proper, whether or not any edges have different color for the two endpoints. Okay. This is our intuition, And now is the more, this is now the rigorous definition. And to do that, I first need to define the class NP. So NP stands for non-deterministic polynomial. Okay? So there are many definitions for NP. The one that is most relevant to us, that this you should think of NP as a class of problems asking for the existence of a solution given an input x, and such that the validity of S as a solution to your problem should be verifiable in polynomial time with respect to the length of x. For example, consider the problem asking if a given graph G has a proper tree coloring or not. This G, the graph, is the input. A solution to this problem will be a proper tree coloring. So it will give you a coloring like this. And now your job is to check if this coloring is proper or not. Check the validity. And this can be done in quadratic time. Because what you can do is that you can simply check every edges. There are at most n square many edges. Check if their color is different. In particular, it's quadratic time. In particular, it's polynomial time. Okay, so this is in NP. And in this case, sharp P will be the counting version of NP. So instead of asking if there exists a solution or not, now you're asking for the number of solutions. In particular, if the number of 0, then the answer is no. In particular, the answer is, if number is greater than 1, then the answer is yes. Okay. So for example, a problem in sharp P will be asking to count the number of proper tree colorings of a graph. Okay. And by the way, so one of the common misconceptions about sharp P is that some people confuse it with FP, which is the class of problem that is solvable in polynomial time. While sharp P, actually, to count this number, it is possible. It is possible that it will take exponential time. In fact, this number of proper tree colorings of a graph, is if you believe in the exponential time hypothesis, then which is some where many people in the computer science do, then it will take at least exponential time to actually compute this number. Okay? So it is not polynomial time. It's it's about whether or not you can verify the solution in polynomial time. It's a bit higher than that. Okay. Okay. Now, without further delay, here is our second main result. What we say is like this. Let us view the Stanleyan inequality as a computational problem. In this case, the input will be a binary matroid M, will be a subset S, S1 up to SD, and integers K, L1, L2 up to LD. So these are all of the input that you need to define Stanleyan inequality. Now, consider the difference between the left-hand side and right-hand side of Stanleyan inequality. It follows from the theorem that this number is a non-negative integer. And then you can ask, oh, Swee Hong, this number is an non-negative integer, right? Then can this number count something? And our answer is that it turns out that no, it's not possible. That this number cannot be a counting problem, at least cannot be a nice enough counting problem so that it belongs to sharp P. Unless the same assumption, NP to the power of NP is not equal to core NP to the power of NP. Okay. Okay. So, in particular, let me let me just mention this before I take questions. So, this is recorded. Okay. I must admit that at first when we found this theorem, I thought we were making mistakes. Why? This is because like this. If you look at the left-hand side and right-hand side, there is an textbook proof actually that both of these numbers belong to sharp P. And it is indeed true that there are some inequalities in combinatorics that we know do not belong to sharp P. But they are usually not in sharp P because the number is too big. Like there are some inequality where they are counting the number of something, the size is like e to the power of 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 n. Then yes, that thing is too big. That thing is definitely not in sharp P. However, in this case, both the left-hand side and right-hand side are already in sharp P. So both of them, the size is already not very big. In fact, we know the size is exponential. The difference, which is supposed to be smaller, somehow become more complicated to count. Becomes harder to actually harder from the complexity point of view. And that, yeah, at first I find it's not believable, but we checked the proof several times, and as far as I know, it's correct. So yeah, so this goes a little bit against our intuition, and that's why actually it took us so long to find it, because like at the beginning we thought this number is in sharp P, where spending like 3 years trying to prove that this is Sharpie, rather than the other way. Okay. Up till here, are there any questions about the statement? Everybody happy? Okay. If everybody is happy, then let me just explain the. Oh, sorry. Let me just explain the assumption that what do I mean by MP to the power of MP not equal to core MP to the power of MP. Okay. And to do that, again, our basic starting point is MP, right? Which is saying that with this the class of problem asking for the existence of solution given an input, and these solutions will be verifiable in polynomial time. Okay. The brother, or maybe the brother of this MP is co-MP. And which is this problem is like the opposite of MP, which is like rather than asking for existence, you ask for non-existence. So the other way to think is that if MP is like, if the answer in MP is yes, then co-MP the answer is no. If the answer for co-MP is no, then the answer for MP is yes. Okay. And in this case, an example will be saying that asking if a given graph is not three-colorable. Okay. And it's known, in fact, there is a rigorous proof that if MP equal to MP equal not equal to this symbol is wrong. So this is showing that MP equal to co-MP. Oh no, this is correct. MP not equal to co-MP implies P not equal to MP. Okay. And to go for one level further, which is our assumption, we need to define this thing that's called the NP oracle. How does it work? I think of this basically, it works like Richard Stanley. How? Like every time you have a difficulty solving a problem, what you do is that, hello Stanley, you ask a problem to Stanley, and then like immediately he will just say like in one step. You think there's one step, is to say that yes or no. Like yes, this problem you do it like this, or no, this problem you cannot solve it like that. Okay. So NP oracle, this is a black box that able to solve any problem in NP in a single operation. Okay, and the complex of MP to power of MP, this is again the problem. It's the same as MP, where you're again asking for existence of solution for input X, except that now you have the existence of Richard Stanley. You can at every step you can just call like one step, that thing called one step to solve a problem in MP. Okay. And co-MP is similar, is where instead of asking for existence, you ask for non-existence. And it is known again that all of these form a hierarchy. That if MP to the power of MP is not equal to core power MP, it will imply MP not equal to core MP, it will imply P not equal to MP. So if for any people who are who has ambition to get $1 million quickly, this is the way to go. Try to prove any of this, $1 million. Guaranteed by the guaranteed by the committee. Okay. Any questions so far about the assumption? That about this assumption that this is the assumption that we use for our theorem. Let's see. Let me go back. Okay, this assumption. Yeah, a question.
So the assumption is not stronger than, like it doesn't imply B equals MP, right? If this is equal, then it doesn't. Like if this is false, it doesn't imply B.
No. If this yes. So no. Yes, that's true. It is possible that this MP to MP, let's say that this is equal. It is possible that P is still not equal to MP. Then in that case, I would say that you will still get $1 million. Just that you don't get it from the millennium price. You will get it from winning Turing prize. Yeah, in fact. And if you are, I think that if you are below 40 when you prove that, you also will win this medal. Like yes, depending on the situation. So $1 million and 25,000 US dollars. Okay. Okay, any other question? Any other question how to get rich? Okay, no? Okay, if you have no question, then I believe that my devil advocate has a question now. Right? Again, let me go back to being devil to my contrarian again. This is like this. Swee Hong, okay, fine. You show that the standing inequality has no combinatorial injective proof, right? But maybe there are still many combinatorial proof that is not done completely by injectively. Like for example, there's the some of this the Lindstrom-Gesell-Vienna argument. There is some determinantal process argument. There is maybe let's say some FKG argument. Maybe those will still work. Maybe those will still prove standing inequality, and we'll say that that is still a combinatorial proof or maybe an elementary proof. Well, today, let us use Sharpie to show that even in those situations, even if we accept that as combinatorial proof, we will still be able to differentiate standard inequality from the other two inequality, the binomial inequality and permutation inversion inequality. Okay, how do we do that? Well, it goes like this. First, let us look at the binomial inequality. Okay. Remember our argument with past swapping injection that shows that this number is greater than this. That argument, in fact, proves something more. That argument actually gives a combinatorial interpretation for this difference. That this is equal to the number of non-intersecting lattice paths for which, number of lattice paths where these paths do not intersect at all. Right? Because if they intersect, then you can just swap the number, you get the element from before. This is the combinatorial interpretation. It is not hard to check that you can use this number to build a Sharpie problem. That this number actually belongs to Sharpie. Okay, so this one belongs to Sharpie. How about the second one? The permutation inversion inequality. For this inequality, there is in fact an injective proof by Miklos-Bona, who showed in 2001, who showed that this AK square is greater than AK minus 1 times AK plus 1. And with that, you can use that it shows that it belongs to Sharpie. But that's actually an easier argument. In the following way, take this unity function. We know that this is equal to Q unknown n factorial, right? This is a very explicit polynomial. Therefore, you can take the multiplication. You can compute all of these coefficients in polynomial amount of time. It's because the product of two polynomials take a quadratic amount of time. Like worst case, like if in case you know how to implement it better, I think you can actually make it a little bit lower, right? But in any case, it's still polynomial. In particular, it's also still polynomial time to compute this difference. And there's another theorem in computer science to show that anything that you can compute in polynomial time belongs to Sharpie. Okay. In conclusion, what we have seen is the following. We have seen binomial, permutation inversion, and standard inequality. The first two, we have just give a quick proof how these two belong to Sharpie. Well, the third one, this thing does not belong to Sharpie. So this gives like a rigorous difference between standard inequality and the other two inequalities. And hopefully this is enough to convince my devil advocate that yes, there is indeed a difference. There is a reason why proving this inequality or proving Mason's conjecture took 50 years. It's not because it's not because combinatorials are not good. Okay. And any questions so far about the result before we go for the last slide? Okay, if there are no questions, then let me finish with one open problem. And this is actually the problem that we mentioned before. That so far we can show standard inequality, right? It does not belong to Sharpie. But if you just make the inequality a little bit easier to prove, like the Mason's conjecture, where we know it's a special case of the standard inequality, unfortunately, I still don't know how to show that this number belongs to Sharpie or not. We strongly believe, let me not change the word strongly. We believe that this number does not belong to Sharpie. Unfortunately, we still don't know how to prove that. That all our techniques that try to prove the standard inequality, because of some technical obstruction, it fails to prove that this difference in Mason's conjecture is not in Sharpie. In fact, let us not even go that far. In fact, let's just, rather than going for matroid, let's do it for graph. So do this for the number of, this IK now is number of forest. That one, I also believe is not in Sharpie. Just that we don't know how to do that. Okay? But in fact, yeah. So if any of you have any idea why these numbers do not belong to Sharpie, or even better, if you have any idea how this number belongs to Sharpie, then we can get $1 million, right? Then please let me know after the talk. Okay, I will love to discuss how to solve the problem, how we should split the $1 million, like 6-4 or 5-5. Okay. And I think that is all I want to say for today. Thank you very much for listening. Yes, question?
So we know that this is not in Sharpie, but like the other problems are in a sense much easier. Do we know when this sort of complication happens?
That's a good question. Yes, we believe it's here. So for this one, for graphs, so for graphs, that is like the more or less the cutting point, where you have to say that where anything that cannot prove, so anything that you can use to prove that Mason's conjecture for graph will definitely not become Schottky. And anything a bit easier than that most likely can be done with Schottky. Most likely can have a maybe not exactly proof injectively, but maybe with some determinant argument with this thing FKG, then they can be done. And in fact, most of them has been done by using exactly that way. This is, I think, the easiest inequality I know that still cannot be done by Schottky. Yeah. Another one is well, depending on how you think, right? So you can think of, let's say, the positivity of Kronecker coefficients, positive Skullberg coefficients. Those are still also unknown if they belong to Schottky or not. And then those are probably also in the somewhere on the bottom. I think maybe somewhere in the boundary. Like we don't know exactly where they are. But hopefully somebody will prove it maybe in 3 years or 5 years. We will know where it is. Yes. Thank you for the question. Yes, maybe both. Yeah,
So maybe I missed it in the slides, but could you say a bit about the history of the definition for combinatorial injection?
That is a good question. So for this injection, yes. So I think the first paper that mentioned this is by Wills, Herbert Wills. But in his context, he actually defined it more as rather than injection, he defined it as a he defined it in terms of the counting version, which is that any numbers that he say is combinatorial, that numbers will be done by so be possible to be done by a polynomial time. And then that definition got changed over time to what the version that we know. Yes. Yes, have a question?
Yeah, I guess I'm just wondering like what your threshold for or basis for like formulating that conjecture, the final conjecture. Because you said, we don't have a proof, right? So it's not that you're like kind of onto an idea that would prove that it's not in Schottky, but like, I don't know, have you done just some experiments or what is the underlying?
Yes. Why do we make conjecture is not belong to Schottky? Yeah. In my case, because I spent from my graduate school until maybe like 2 years ago, so 7 years, I tried to prove this. I tried to prove this injectively. I tried to find an injective proof of this result for the case of graphs. And I must say that we failed that one.
But I mean, like not, failing to find an injective. I mean, maybe you just haven't like come up with the right one. It's a formal conjecture, right? To say like, no, it's not in Schottky, and I guess, I don't know.
Actually, I completely agree with you on this, that it is possible that this conjecture is wrong. And in fact, I'll be much happier to see that this is wrong. Like if you can show it's in Schottky, I'll be much happier that it's not in Schottky. Because well, maybe kind of both. Okay, on one hand, I'll be less happy because if it's not in Schottky, I will feel a bit vindicated that I spent 7 years trying to prove this and try to prove in Schottky, try to find a combinatorial proof, and I failed. So maybe I'm not that stupid. On the other hand, I'll be even happier that I find some of this. If this thing can be done by combinatorics, can be just done by injective, that will be beautiful. So in a way, I think the worst situation is that if you cannot do anything at all. That if these things stay open, that is the worst. The worst part. The worst option. So hopefully somebody, maybe us or maybe somebody else, can finally solve this one way or another. Yes, question. Sorry.
What is defect?
Defect. This means that's the difference. This difference of this number. So another way to view this is this, right? Both numbers as combinate interpretation. What is the combinate interpretation for their difference? That is another way to view this. Yes. Yes, question?
Do your investigations in this area have any bearing on the problem of like classifying which sequences of numbers could be the independence numbers of the graph?
That is another good question. In a way, yes, but it gives you a necessary it gives you a sufficient condition to say something is not in. But is it like exactly characterize exactly all these numbers? That is still a very, I would say, very difficult problem.
Yeah, like by analogy, maybe like, so for example, the G conjecture, G theorem, exactly tells you what sequences are F vectors of some social polytopes.
Uh-huh.
And it's more than just, like some unimodality. I mean, unimodality is kind of part of it, but there's another, it's a kind of exact description of inequalities that determine F vectors. So like you could hope for that for these I sequences, but is what you're showing here that maybe it's too much to hope for that, or is it maybe not related? I don't know.
So I guess what I can say is that maybe not exactly I, but let us go for the one that we know how to prove, which is let me go back. B. We know that this sequence is actually now that we know that this sequence is not in sharp P, what it means is that any of the description for any of your if and only condition for this BK will definitely be very complicated.
Okay.
Be very complicated enough, like it cannot be checked in polynomial time, for example. Right? Much worse than that. It's not even polynomial hierarchy. But anyway,
Okay.
yeah, you're welcome. And yes, question again, yes. No, go on.
So this, if you have like strong log-concave and you have like ultra log-concave, they would imply log-concave, but
Yes.
they don't imply combinatorial interpretation necessarily. So is it easier to find a combinatorial interpretation of strong log-concave in some cases?
That is a good question. In the sense that let us go back to this Mason's conjecture, right? So one thing that I didn't mention, which is thanks for letting me know. Where is it? Mason's conjecture. Yeah, in fact, Mason's conjecture, he conjectured that this is actually ultra log-concave. So there's an extra constant 1 + 1 over k times 1 + 1 over n minus k. And proving either one of them to not have combinate interpretation, the hardest one to prove that it has no combinate interpretation is this one. It'll be a bit easier if you can. So that's actually a theorem in complexity theory, that if you can show that this thing is not in sharp P for some constant C bigger than 1, strictly bigger than 1, then let me think the direction. Okay, if you can show that this thing has no combinatorial interpretation, it also implies that there is no combinatorial interpretation if you put any C here greater than 1, strictly greater than 1. Okay, so this one, the one that I put here, let me go back. This conjecture, in a way, is like the ultimate form. As we say, if you only can, let's say you put it for graph, that is the ultimate, I would say that is like the ultimate holy grail for all of this approach. Once you can do that, once you show that in some sharp P, then everything else are also not in sharp P. In a way, yeah. But of course, it can also be not in sharp P. In that case, then I'll be even happier. Then a nice combinatorial proof of this. How can we get that? Yes. Any other question? Yes, sir.
Yeah, your other two examples, the binomial coefficients and the inversion, do those come as I of something if I look at some nice families of graphs? Like, are they actually particular nice cases of this, or?
That is a good question again. Yes. So you're asking like if this example can be written as this maybe let's say Lagrangian polynomials of some matroids. The answer is yes. The first one and the second one, I'm not so sure, but the first one definitely. Second one, not exactly Lagrangian polynomials, but if you go even further, you go to this. If you're happy with this nav divisor of some of this Taylor package, then the answer is yes. So all of them actually belong to the same class, but somehow these two is not complicated enough to be in outside of sharp P. This is the one that's complicated enough in sharp P. Yes. Any other question? Feel free to. And maybe I should check the.
Are there other examples other than the two given?
You mean the one in sharp P or the one not in sharp P? Okay. So for things in sharp P, there is there are many more examples. The way I do it is I just go to this list of Stanley, all of this positive combination interpretation, went through one by one. The one that we know has been positively accepted by. Okay, there are some of them that are arguable, like some people say that it is combination interpretation, some people say it does not. But the one that has been commonly accepted, they all belong to sharp P. The one that's not in sharp P, we have many conjectures of things not in sharp P. But so far, I know only 3 results. 3 results that that show that some natural number in combinatorics is not in sharp P. The first one is that the characters of an irreducible character symmetric group is known to be not in sharp P. That was done by Panova Greta Panova, Ickenmeyer, Igor Park, and Greta Panova. The second one is the Stanley's inequality proposed set, also known not in Sharpie. That is by me and Igor Park. And this is the third one, again by Igor Park and somebody else. Well, all of them by someone person, yes, but hopefully it will change soon. Hopefully this somebody we can show something else not in Sharpie and not only by this group of people. Yes. Any other question?
In that case, let's thank Swee Hong again.
Thank you very much.